Hello, this is Arkasha from MCAT Simplified. Today we're going over the Zeroth Law of Thermodynamics. Now this law states that if you have two systems A and B that are both in thermal equilibrium with another system C, then that implies that systems A and B are also in thermal equilibrium with one another. Okay? Now the significance of this law is that it first of all allows us to define what temperature is, okay? And it also really forms the foundation for things like thermometers and measuring temperature and things like that. Now, diving a little bit deeper about the implications of this law, the first thing is this idea of thermal equilibrium. And again, thermal equilibrium is basically, if say you have a system A and it's in thermal equilibrium with system B, that's suggesting that there is no heat flow between these two systems. And that means that these two systems have to have the same temperature. Alternatively, or rather inversely, if there is heat transfer between two systems, whatever they may be, then that means they cannot be at the same temperature because they're not at thermal equilibrium. And so coming out of that, we can also see that this law helps us to define a property, right, that can describe basically if something is in thermal equilibrium. Okay, or if systems are in thermal equilibrium. And that property happens to be temperature, okay? And temperature is a scalar quantity, so it has a magnitude but no direction. And then additionally, temperature is a state function. So a state function is basically a function that only depends upon its initial state and its final state. So if a system goes from an initial state to a final state, okay, that can be described by a state function, then all you need to know is what the final endpoint is and what the starting point was, and you can determine what the change was, the magnitude of the change, okay, as well as the direction of the change, right? So temperature, if you know the final temperature and the starting temperature, then you can simply subtract them and you know what the temperature change was, okay? And this is in opposition to what are called path functions, which are basically dependent on how you get from point A to point B, the specific process of getting from point A to point B, because that will actually change the value of that path function. Whereas temperature as a state function doesn't matter. It doesn't depend on the path taken. The path taken can be 100 different ways from getting from point A to point B, but as long as the final state and the initial state are the same, then the value of that state function, in this case temperature, will also be the same. So temperature is a scalar, and then it's also a state function. And this is really important because for one thing, the first and the second laws of thermodynamics are both dependent on this idea of temperature, okay? And then of course, with this idea of temperature being a property that determines whether something is in thermal equilibrium or not, that also allows for us to create temperature scales, okay? And remember, there's the Celsius scale, there's the Fahrenheit scale, and then of course there's the Kelvin scale. And it's important to be familiar with these and understand how to go from one to the other. But the point here is that it's really this law that allows for those scales to even exist in the first place, okay? Now, another important application is the idea of a thermometer, right? So this idea of thermal equilibrium in systems, having heat transfer or being in thermal equilibrium or not with one another allows us to understand this concept of a thermometer, all right? Because imagine you have three systems, or three bodies in this case, right? You have a cup of coffee with your warm coffee, you have a metal spoon in that coffee, and then you have your thermometer. And we know with the Zeroth Law of Thermodynamics, right, that if we put the spoon, the metal spoon in the coffee, we know that eventually those two, the coffee and the spoon, there will be heat transfer from one to the other, probably from the hot coffee to the cold spoon, okay? And they will eventually be in thermal equilibrium. The temperature will be the same. And then if you put the thermometer into the hot coffee, we know that the hot coffee and the thermometer will also equilibrate with one another, and the thermometer will show us the temperature of that coffee. But then, because thermal equilibrium is transitive, okay, we know that since system A, in this case the coffee, and system B, the metal spoon, have the same temperature, they're at thermal equilibrium, then we know that the thermometer, right, which we see as like physically in contact with just a cup of coffee, okay, it must also be in thermal equilibrium with the metal spoon, Okay, so all must be in thermal equilibrium in this case. Now, this law will also provide insight into different heat transfer processes. And there are three major ones that we really want to understand. The first of these is conduction, right? And conduction is heat transfer through direct contact, okay? So imagine you have a hot stove and you have a metal pan. You want to cook something. You put it on the hot stove and the metal will heat because there is direct contact between the hot stove, which is at a higher temperature, and that cold metal. So there is a heat transfer. Now, convection is heat transfer through fluid movement. And this is a little bit trickier to understand, okay? So fluid movement refers to the movement of both liquids and gases. Remember that. And what you also want to remember is that when a fluid is heated, the fluid is going to rise. So there might be areas of the fluid that are hotter than others. So the hot areas will rise and the cold areas will sink, so to speak. So initially, if we're going to follow through with this example of the pot, we have water in this pot and we put it on the hot stove. And initially, there is going to be heat transfer via conduction from the hot stove to the metal. And then there is going to be heat transfer via conduction from the metal to the water initially. And so some of those water molecules are going to heat up. They're going to start moving. Their kinetic energy is going to increase. And as we know, that hot water is going to start to rise. And as you might imagine, as the hot water rises, it's taking heat with it. And so that is convection, okay? Because it is heat being transferred via movement of fluid. That hot water is moving up. It has this kinetic energy and it heats its surroundings as it moves up. And so that is convection, okay? And the same thing can be true, to really hone this point in, with like a campfire. So imagine you have a campfire, you're sitting there getting warm. You're not really touching the flames with your hands, but you're getting warm, right? And that's because the fire, okay, is actually going to be heating air around it, right? And that air, the hot air, is going to start to rise. And it's the hot air, it's the movement of that hot air that is going to be warming your hands, okay? That's convection, right? That's one of the ways with a campfire that you're getting warm, okay? Now, radiation is the third one, which is heat transfer via electromagnetic waves. And so continuing with this example of the campfire, the other way that you're getting warm is that there is actually electromagnetic radiation emitted by the fire, and that is also transferring heat to you. So these are three different ways in which heat can be transferred. And it's really important, especially for the MCAT, to be familiar with these and the differences between them. And remember that per the Zeroth law, essentially, the heat flow is going to stop when thermal equilibrium is reached, when the two systems or whatever systems are at the same temperature. And that's it for the Zeroth law of thermodynamics. Check out our website at mcatsimplified.com.